NanoHub U, online instruction.
Hey everyone, welcome to lecture 115. Continuing on the last lecture where we discussed what are the basic ways to set up the solution to the Maxwell eigenproblem. Now we're going to go into more details about how do we actually solve it. So there is one key challenge in this sort of problem. As you recall, we were using fast Fourier transforms because we could naturally represent some of the components of the Maxwell eigenoperator, which is a curl operator, in the Fourier domain. But then we also found that that also forces us to put epsilon inverse in the Fourier domain. Unfortunately, epsilon inverse could very easily become discontinuous in the Fourier domain, which could risk our convergence. So we can actually perform a physically motivated averaging process for epsilon inverse, which amounts to assuming that E parallel is continuous across boundaries, and then D perpendicular, the displacement field, is continuous across boundaries. So once we have that information or assumption into our model, which is kind of represented by this equation here, and it's based on this projection operator where Ni is the normal direction, and we've constructed it as an outer product of those two ends, then we get actually much more reliable result. And you can see on the right-hand side, if we had no averaging, we kind of get this erratic reduction in error as we go to higher resolution. But then if we use the epsilon averaging, we actually get it to converge much more quickly and reliably. So that's actually a big advantage for us. And then in terms of implementing the actual solution in more detail, remember we only want to work with p-bands because that's much more computationally efficient and reduces our storage. So we have two choices that we can really consider. First is conjugate gradient minimization of the Bloch-Rayleigh quotient. And then the second is called the Davidson method, which is related to the Lanczos methods. And of course, probably most of you don't know what that is, which is fine, but I'll explain that right now. So the Rayleigh quotient is oftentimes used in understanding the variational principle to minimize the wave function or the energy of a particle. And so it amounts to writing down an energy or lambda naught in general, which would be kind of the minimum of the ratio of taking the outer product of y naught, some sort of trial function with your A operator, divided by the outer product of y naught with the B operator, which goes into the eigenproblem. Recalling that, of course, there was this extra like auxiliary matrix in the eigenproblem as we had formulated it. And then what you do in the Rayleigh-Ritz algorithm is you first would minimize for y naught, which is basically your first trial function. And then you would then create a new y1 that would be a trial guess that is completely orthogonal to y naught. So that means you won't allow any y naught components because you're assuming that every new solution is orthogonal to the previous solution. And then you can build that up by a step-by-step minimization. And you can either do one at a time or you can do it in small blocks at a given time until you get to p-bands, however many bands you need. So you're not necessarily strictly limited number of bands. And so here we've actually written out like some of the equations for Bloch-Rayleigh quotient minimization. So we choose y in an n by p matrix, and then we minimize the trace of the outer product of y dagger with A and y, subject to the constraint that y dagger by is equal to 1. And so this is essentially a generalization of that Rayleigh-Ritz method that I just showed you, just doing it in a block configuration that I mentioned earlier. And then we can also perform an unconstrained minimization by transforming to a z basis, which can make things a little faster for us computationally, rather than having to strictly enforce this condition directly. Now, the second method that I mentioned that we can use is iterative eigensolver with either steepest descent or conjugate gradient method. And so in the steepest descent method, you can kind of think of it like climbing up a hill. So if you are climbing up a hill, you have the advantage, not only do you know your position, but you can also look at the gradient or kind of the slope of the ground below you. So if you know you want to get to the top of the hill, it makes sense that you just go in the direction that has the steepest slope until you get all the way to the top, right? And so that's what it amounts to. But in the conjugate gradient method, it's related, but a little more sophisticated because you would actually not only use the current gradient, but you'd also remember the prior steps that you took in climbing up that hill. And so that's kind of illustrated here. And you can see that actually it allows you to take like just a finite number of steps, but very quickly to ascend that hill, because in this case, unlike the real hiker, you actually have the ability to take either very small or very large steps. You can calibrate the step size very well to the given problem. So for some types of problems, which are fairly quote-unquote easy to optimize, so-called convex problems, then these actually behave beautifully. In other types of problems, it's a little more challenging. So then we'll explore that next time.